All right. Hi. So yeah, now we have Sultan Orazbayev. He's going to be giving a talk on titled Record Linkages on a SLURM cluster with Dask. And Sultan is a social scientist interested in questions related to economic growth, migration, and social networks. So welcome. Thank you, Sultan.
Thank you very much. So this is my experience of working with Dask for a particular project. It's a joint academic project where we link individuals across different census waves. So the outline of this talk is I'll just do an introduction to record linkage, how it works, the core of it, give you a sense of the project outline, and then elaborate on the applications of Dask and experience of actually running Dask on the cluster. And so record linkage, what is it? The simplest possible way to explain is that imagine you have similar records of a person or entity. It could be a company or some other object of interest. You have it recorded in different data sets. So there are different features associated with that entity. And you are interested in combining these records, right? So that's record linkage or entity resolution or data deduplication. Now, how is this different from a simple merge, right? So ideally, of course, if you have a persistent identifier across these different data sets, you would use it for merging, but in real life, what typically happens is there is no merge key, and in addition to that, records contain noisy data. So you will need to develop some procedures in terms of saying which records are similar and which are not. Right? So I'll show you a quick example, and this will use the Dask datasets that are generated artificially. And the dataset is going to be very simple. It's going to be first name, last name, age, and occupation. Now, this is a sample data set with 5 individuals. So this is a pandas data frame. And what we're going to do next is split it into 2 data sets, and imagine that we have only part of the information in each one, right? So, for example, in data frame 2, we have only first name, occupation, and age. In the other one, we have first name, last name, and age, and we're interested in combining them. So in this example, we actually have the identifier. So that means, simple merge will give us the data of interest. But if we pretend that we don't know this identifiers or it's not available, right? What can we do? So with this simple example, you could actually see first last name combinations that they are uniquely identifying individuals, and or first name and age, and use that to merge people. But again, in real life, it won't be as simple. So how are we going to compare this? There is a package, there is a record linkage package that allows us to make these comparisons, and the simplest possible way is to do full indexing. So compare all possible combinations of records and evaluate them based on similarity. So if we do that, you can see that the indexer computed by this record linkage is simply forming all pairwise combinations of records, right? So all 5 records in the first data frame and 5 in the second data frame. And now we need to also define how we are going to decide whether 2 records are similar or not. So in this case, we can look at similarity in terms of strings, so Yarrow-Winkler method of computing similarity, and then differences in ages. So the record linkage package has a lot of different metrics for strings, numbers, and other data types, but here we can just take a look at these two. And if you actually compute it for these pairs that were formed using the information in the first and second data frames, you will get similarity metrics for all combinations of records. And you can see here, for example, that record 0 in the first data frame and record 0 in the second data frame has perfect similarity in terms of names and age, which is as expected because it's referring to the same individual. And looking through the others, you can see that the closest, the next closest is record number 3, and by inspecting it, you can see that it's similar name, so it shares a lot of the same letters. So, you know, in some contexts, this could be a different spelling of the name or the same name recorded with some noise. So it potentially could be indicating a similar entity. And to examine this more systematically, we could figure out a way of aggregating those similarities. So in this case, I'm just going to sum them and define some arbitrary threshold based on which I will think that these matches are of good quality or in which I have high confidence. And once you do that, you can see that we end up with recovering all 5 of our individuals, which is expected in this example. And similarly, you can check that you know, matches with low confidence, it's pure noise. You don't get any true matches there. Now, alternatively, you can also inspect visually that the matches that you obtain, they give you the same individuals. So the first name and ages, they are matching across 2 data frames. Here there was a extra noise introduced in the age variable just to make this a bit more challenging, but it's basically rounded to the nearest multiple of 5. Now you can, everything so far has been done in pandas data frame, but you can do the same thing with Dask data frames. And here I'm just increasing it slightly to bigger data. Now it's 5 individuals per partition, and there are 3 partitions, right? So this is what, for example, data frame 2 would look like. And exactly the same code as before, but wrapped in a delayed API, allows you to scale the same computation to multiple partitions, right? So you can now do a very simple thing where you say, okay, let's imagine each partition is a separate data frame and just compute all pairwise combinations. This, of course, is not practical in real world examples, but for now, this is just to show you that the way Dask delayed could be used here. So obviously, in real world example, you would want to reduce the number of combinations. So there are various techniques around that, but this is what Dask would compute for this simple example. So there are 3 partitions of the data frame, and if we're doing all pairwise combinations of partitions, you would end up with 9 computations, 9 tasks, right? And if you actually compute it, you will see that you are able to recover all the matches correctly. So we had 5 individuals, 3 partitions, so 15 records identified correctly. Now, in real life scenarios, you will have extra complications. So one complication is scale of the data. So it will not be feasible to do all pairwise combinations, because everything I've shown so far was all pairwise combinations of records across data frames, and then all pairwise combinations of partitions as data frames. So that's a lot of computations. You wouldn't be able to do it in most cases. There are further complications like duplicate records or missing records. So it's possible that you will be looking for a record where there is none. There are non-unique links. And then there's also ambiguity on what exactly constitutes similar records. So how do you do that? And all of this is complicated by the noise in the data. Now, the specific context for the joint project I was working on is linking of US census records across time. So this is data is provided by IPUMS USA, and there is a link here you can explore. And it's a task that multiple teams are trying to solve with different algorithms. So I'm listing some of them, but in terms of our team, yeah, I'll elaborate on that separately. But to give you a sense of what the data looks like, it's as follows. It's as follows. So this is an image of a census record which contains a number of features for every individual, like their gender, and then their age, their place of birth, name, place of residence, and so on. And you're seeing the image records, but all of this has been digitized and provided in tabular form by IPUMS USA. So we don't need to do any of this recognition here, but we have a variety of information about individuals, and the task for us is to link them across different waves of census. So, you know, John Smith in 1850, we need to find the same John Smith in 1860. So it's a record linkage problem, but it's a very large scale problem. And our team, so this is a joint work with Andres Gomez-Livano and Mate Hartog and Frank Nefke. What we do differently from other approaches is we try to leverage the network techniques to link these records. And this workflow, these algorithms, they will involve a lot of operations on very large and mostly sparse matrices. So very large means that matrix shapes are about 100 million by 100 million. Now they are mostly sparse, so there will be dense regions because of you know, the way we compute things and properties of the distribution of individuals across across the data. But to give you some sense of challenges is the following. So if you were to do to initiate this array, and of course this is a dense array, this is roughly the memory requirement, right? So 74 gigabytes for 10,000 by 10,000. Sorry, 100,000 by 100,000 matrix. The fact that it's sparse means that the memory requirements on this particular array would be smaller, but there are many operations that have to happen, and at times it will exceed memory. So it was not feasible to do it on a single machine, and Dask was very useful for parallelizing and scaling things. So this is a picture created by my colleagues, and this shows you distribution of individuals in US in 1870, so roughly where people lived. And you can see that the West Coast is not as populated relative to, say, 1940, where the US is getting more and more populated. So I skipped a whole lot of waves, but the calculations we have allow us to track individuals across this 100-year period within the United States at a very high resolution in terms of space, in terms of various variables like their occupations and household composition, their neighborhoods, and so on. Now, specifically talking about Dasks, where the uses, the first use was to go beyond the single machine, and these operations with matrices required basically large memory computations. So here we use Dask to construct objects with delayed API and then apply custom logic to these operations. And it's early on we tried Dask arrays, but the support for sparse arrays was not that great. At various points, it would attempt to densify the arrays, and that would lead to memory problems. So in the end, we started using the delayed APIs because it gave us greater flexibility in terms of how to write the code. And the second use of Dask was to speed up parallelizable tasks. So because of the large number of variables, for many operations, you want to keep the core data light. So there would have to be a lot of merges that would have to happen. So sort of reducing the data and then attaching relevant variables as needed. So Dask was very useful in these types of relatively simple and parallelizable tasks to scale them up and have very quick iteration speed. So the calculations were done on the canal cluster. So this is a SLURM cluster, and it operates on the queue system. And because of this queuing system, it was not very easy to create batch jobs. So it wasn't easy to guarantee simultaneous resource allocation for the workers. So a common problem would be, for example, you submit something with that a code that has a Dask job queue built in, and you submit it as a batch job. The Dask job queue requests workers, but then these workers are provided only with some delay, and that causes some problems downstream. So more recently, there's head jobs for SLURM cluster, but it's still not easy to implement it with Dask. So it's yeah, I guess it's a feature that might be supported in the future, but right now with SLURM cluster, it's mostly for interactive work, and Dask job queue makes it very easy to do that. But this combination of queuing system and sort of large queues in the system makes it difficult to have batch jobs that that would utilize this scaling features of Dask. And yeah, that's all I have for you, and thank you for the attention. Just to acknowledge the fact that this is a joint work, and the core team includes the collaborators, so Andres, Mate, Frank, There are other members of our research lab that are involved in more specific analysis, and I encourage you to visit our website and learn more about the work done at the lab. Computations were done on the cluster, and census data was provided by IPUMS USA. So yeah, that's all on my end. I'm happy to answer any questions.
Great, thank you, Sultan. Do we have any questions? So I have, I guess, one quick question. You mentioned the example of where you have like a Joe Smith in 1850, and then you're trying to connect that to a Joe Smith in 1860. Is the problem again that, you know, you have people that might give their data and it's just not carried forward or stored in the same way for that same user?
So that's a good question. There are several things. So the original data is all in terms of images. So when this data was transcribed into this, so digitized and transcribed into this tabular form, there are recognition errors, there are typing errors, and that means that it's difficult to rely completely on the accuracy of the data. So it's possible to have, for example, John Smith with a gender recorded as female, you know, or Samantha who will be male. So these types of errors, or you could see, for example, a person who is, according to the raw data, is 3 years old, but his occupation is engineer, and you know, he has several children. So there are these types of transcription or noise, I guess, in the data. But another more challenging problem is the fact that there will be many candidates. So one John Smith will have, you know, potentially 1,000 other John Smiths next wave. So you need to find a way to resolve this sort of ambiguity in terms of who is who. So the more challenging task is not finding candidates, it's resolving candidates. And I did not talk about that, but this is something we're publishing as a separate paper. So hopefully that will be available soon.
Thank you. There's another question we have, which is, how did you interact with SLURM from Dask? Did you use Dask Gateway or Dask Job Queue?
So it was Dask Job Queue, and yeah, it's very easy to use it. The tricky part, of course, is getting the resource requirements right to enable this interactive work, because basically if you request too many workers or workers with very high resource requirements, you might end up sitting and waiting for those workers to appear. But short answer is Dask Job Queue. It's very good.
Any other questions pending? All right, well, thank you very much. I guess we'll see you on Slack.